supports the basic mathematical operations you would expect for all of the number types: addition, subtraction, multiplication, division, and remainder. The following code shows how you would use each one in a let statement. Each expression in these statements uses a mathematical operator that evaluates to a single value, which is then bound to a variable. Appendix B contains a list of operators so that Rust of all the operators that Rust provides. As in most programming languages, a Boolean type in Rust has two possible values, true and false. Booleans are 1 byte in size. The Boolean type in Rust is specified using bool. For example, let explicit type annotation. The main way to use Rust values is through conditionals. Boolean values through conditionals. As an if expression, we'll cover how such as an if expression. We'll cover how if expressions work in Rust in the control flow section. The character type. So far, we've worked only with numbers, but Rust supports letters too. The Rust's char type is the language's most primitive alphabetic type, and the following code shows one way to use it. Note that char or car literals are specified with single quotes as opposed to string literals, which use double quotes. The char type is 4 bytes in size. Wow. 4 bytes. That's in Java it's 16-bit, so it's 2 bytes. And represents a Unicode scalar value, which means it can represent a lot more than just ASCII. Accented letters, Chinese, Japanese, Korean characters, emoji, zero with spaces are all valid character values. Zero with spaces are all valid character values. Unicode scalar values range from 4 hex to D7FF, but yeah. So every 16 is 4. So this is a byte. These are 2 bytes. 2 bytes. 2 bytes. Sorry, 1 byte. And 1 byte. 1 byte. 1 byte. And then 1, 2, 3. What need is the 4? However, a character isn't literally a concept in Unicode, so your human intuition for what a character is may not match up with what char is in Rust. Let's discuss this topic in detail. Storing UTF encoded text with strings in Chapter 8. Compound types. Compound types can group multiple values into one type. Rust has 2 primitive compound types, tuples and arrays. The tuple type. A tuple is a general way of grouping together a number of values with a variety of types into one compound type. Types have a fixed length. Once declared, they cannot grow or shrink in size. We create a tuple by writing comma-separated list of values inside parentheses. Each position in the tuple has a type, and the types of different values in the tuple do not have to be the same. We've added an optional type. We added optional type annotation in this example. Okay. Yeah, they don't have to be. The variable tuple binds to the entire tuple because a tuple is considered a single compound element. To get the individual values out of the tuple, you can use pattern matching to deconstruct tuple values like this. Tuple is this one. Let x, y, z equals the tuple. Value of y is, yeah. This program first creates a tuple and binds it to the variable 2. Then uses pattern with let to take top and turn it into 3 separate values, x, y, and z. This is called destructuring because it breaks the single tuple into 3 parts. Finally, the program prints the value of y, which is 6.4. In addition to destructuring through pattern matching, we can access tuple directly by using a period, followed by the index of the value. I'm guessing this is all resolved at compile time. Like x would be kind of like a struct in the memory, and this would be the first offset 0 of the struct. This is offset 1 in the struct. But it can directly show, like this is 32-bit, so this is at compile time. This will be assigned an address, this will be assigned the next address after 4 bytes. This will be assigned 8 bytes, this will be assigned 1 byte. So this will be, if this is at address, let's call it Q, this will be Q, let 500, the address at Q, and this would be Q plus 4 bytes, and this will be Q plus 12 bytes. Yeah, so give this good. Okay. This program okay. As most programming languages, the first index of a tuple is 0. Sure. Another way to have a collection of multiple values is with array. Unlike a tuple, every element of an array must have the same type. Arrays in Rust are different from arrays in other languages because arrays in Rust have a fixed length, like tuples. Fixed length. Different, yeah. In Rust, the values going into an array are written as a comma-separated list inside square brackets. Okay, just like list in Python. Arrays are useful when you want your data allocated on the stack rather than on the heap. We will discuss stack and heap allocations in chapter 4, or when you want to ensure you always have fixed number of elements. An array isn't as flexible as a vector type, though vector is a similar collection type provided by the standard library that is allowed to grow or shrink in size. If you're unsure whether to use an array or a vector, you should probably use a vector. Chapter 8 discusses vectors in more detail. An example of when you might use an array rather than a vector is in program that needs to know names of months and year. Very unlikely that such program will need to add or remove months, so you can use an array because you know it will always contain 12 elements. You would write an array's type by using square bracket, and within the square brackets include the type of each element, semicolon, and then the number of elements in the array. This seems like a special construct in Rust. I wonder if here I32 is the type of an element after semicolon, The number 5 indicates the array contains 5 elements. Writing an array's type this way looks similar to an alternative syntax for initializing array. If you want to create an array that contains the same value for each element, you could specify the initial value followed by a semicolon and then the length of the array in square brackets as shown here, 3, 5. The array name A will contain 5 elements that will all be set to 3 initially. This is the same as writing as 3 5 times, but more concise way. An array is a single chunk of memory allocated in the stack. You can access the elements. Okay. How about, is it always, yeah. An invalid array elements access. What happens if you try to access elements in the array? You can change the following compile time, which will compile but exit with error as it runs. Will compile but exit with an error when it runs. Is it initialized to 0 though? I'm guessing they're always initialized. Let the compilation didn't produce any. Oh yeah, because you can't allocate an array aside from creating the array explicitly, right? The compilation didn't produce any errors, but the program resulted in a runtime error and didn't exit successfully. When you attempt to access the element using indexing, Rust will check that the index you specified is less than the array length. If index is greater than or equal to the array length, Rust will panic. This is the first example of Rust safety principle in action. In many low-level languages, this kind of check is not done, and when you provide an incorrect index, invalid memory can be accessed. Rust protects you against this kind of error by immediately exiting instead of allowing the memory access and continuing. Chapter 9 discusses more of Rust error handling. Okay, functions and control flow remain. Is ownership or ownership is long? Okay. Functions are pervasive in Rust code. You've already seen one of the most important functions in the language, the main function, which is the entry point of many programs. You've also seen the fn keyword, which allows you to declare new functions. Rust code uses a snake case as conventional style function and variable names. Snake case letters are lowercase, underscore separate the word. Here is a program that contains an example function. Okay, function definitions in Rust. Start with fn and have a set of parentheses. What? Return type. Function definitions in Rust start with fn and have a set of parentheses after the function name. The curly brackets tell the compiler where a function body begins and ends. We call any function we've defined by entering its name followed by a set of parentheses because another function is defined in the program, it can be called from outside the main function. Note that we define another function after the main function in the source code. We could have defined it before as well. Rust doesn't care where you define your function, only that they're defined somewhere. Let's start a binary project, name functions to explore functions further, place another function example in the source main and run it. You should see the following out. Let's do that. Okay. The lines execute in the order in which they appear in the main function. First, hello world message prints, then another function is called and its message is printed. Functions, function parameters. Function can also be defined to have parameters which are special variables that are part of a function signature. When a function has parameters, you can provide it with with concrete values for those parameters. Technically, the concrete values are called arguments, but in casual conversation, people tend to use the words parameters and argument interchangeably. What's the distinction? Technically, concrete values, the values are the arguments, but the parameters are parameters. Okay, interchangeably for either the variable in a functions or the concrete values passed when you call a function. The following rewritten version of another function shows the parameter looks like in Rust. Another function, okay. Let's do that. What is wrong? Okay, the function value x is 6. The declaration of a variable has one parameter, type of x specified as I32. When x macro puts 5 where the pair of curly brackets were in the format strings. In function signature, you must declare the type of each parameter. This is a deliberate decision in Rust design. Requiring type annotation and function definitions means the compiler almost never needs you to use them elsewhere in the code to figure out what you mean. When you want a function to have multiple parameters, separate the parameter declaration with commas like this. Okay. This example creates a function with 2 parameters, both of which I32. The function then prints values in both of its parameters. Note that function parameters don't all need to be the same type. They just happen to be the same in this example. Okay, let's try running the code, replace the current. Okay. I don't need to do that. Because we call a function 5 is passed as a value for y, the 2 strings are printed with the values. Okay. Function bodies contain statements and expressions. Function bodies are made up of a series of statements optionally ending in an expression. So far, we've only covered functions without an ending expression, but you have seen an expression as part of a statement. For Because Rust is an expression-based language, this is an important distinction to understand. Other languages don't have the same distinction. So let's look at what a statement and an expression are and how how their difference affects the bug. Okay, so the expression has a value at the end. We've actually seen statements. Statements are instructions to perform an action, do not return a value. Expressions evaluate the resulting value. Okay. Creating a value, let as a statement. Okay. Function definitions are also statements. Entire preceding example is a statement in itself. Statements do not return values, therefore you can't assign let statement to another value. You will get an error. Okay. Does not return value. This is different. Okay. Assignment returns a value. In those languages you can write x equals y equals x 6, and both x and y will have 6, not in Rust. Expressions evaluate something and make up most of the rest of the code. You will write in Rust. Okay. Expression. Okay. Calling a macro is an expression. Calling a function is an expression. Calling a macro is an expression. The block that we use to create scopes is an expression. For example, okay, so this is an expression and returns, yeah. X plus 1, line without semicolon at the without semicolon at the end, which is unlike most of the lines you've seen so far. Expressions do not include any semicolon. If you add a semicolon to the end of an expression, you turn it into a statement, which will then not return a value. Keep in mind as you explore. Okay. Functions with return value. Functions can return value, code calls them. We don't name return values, but we do declare their type after an arrow. In Rust, the return value. Why did they not stay consistent and use dot for the type? Colon for. Is there some carrying that happens here? Let's check. Aesthetic, as often pronounced as has the type. Basically, there are two contexts when the return value of a function can be mentioned. Okay. Using colon instead of an arrow wouldn't hurt readability in the first case. Yeah. Would definitely do so in the second one. And makes perfect sense to have the same symbol in both contexts. Yeah, simply type lambda. Oh, okay. Okay. Functions with return values can return, okay, arrow, synonymous with the value of the final expression of the block of a body of function. You can return an early form of function using the return keyword and specifying a value, but most function returns the last expression implicitly. Here's an example. Okay, 5, I32, 5, okay. There are no function calls, macros, or even let statements in the 5 function. Yeah, just number 5 by itself. It has a perfectly valid function in Rust. Note that function return type is specified to I32. 5 and 5 in the function's return value, which is y. The return type is I32. Let's examine this more in detail. There are two important bits. First, the line let x equals 5 shows that we're using the return value of a function to initialize a variable. Because the function 5 returns a 5, that line is the same as following x. Yeah, but this is at runtime, not at compile time. Second, because we couldn't have known what the value is, could have been. Okay. The 5 function has parameter and defines, okay, has no parameters and defines no semicolon cause an expression, sure, +1, x +1, sure. Running this code will print the value of x is 6. But if you place semicolon at the end of line chaining expression, we'll get an error, of course, because now you're so. This is yeah. Void, is it called a void type, a unit type? Yeah. File unit type. Empty tuple. Okay. Definition says it will return, but statements don't evaluate a value which is expressed by an empty tuple. Therefore, nothing is returned, which contradicts the function definition and results in an error. In this output, Rust provides a message to possibly help rectify this issue. It suggests removing semicolon. Yeah. Okay, that's the end of functions. Control flows. Control flow. Control flow or flow control? Flow control. Not control flow. Ah. It's the flow of the control, okay? Flow control. Okay. But I guess it's flow control. Flow of control is the order in which instructions, yeah. It should be control of the flow, right? Because you control where the flow goes. Can I finish 10 modules tonight? Possible. I feel like I have read this before. Enums match if let precise. Okay, concise, sorry, not precise. Managing common collections, hash maps, error handling. Yeah, I should probably be able to finish up till error handling tonight. Let's continue. You're back. Let's check the news quick. Electoral village votes for Biden. Well, yeah, that's how it works. Trump says he will leave the White House if, yeah, of course. Biden to face test over access to sensitive information as he inherits Trump's secret server. Sure. Rebranding, but not reinventing Trump's China policy. Okay. Why Biden shouldn't extend an olive branch to the Republicans? Ah, come on. He'll travel to Georgia to support Republican Senate candidate in runoff election. Okay, that's understandable. Oh, is this a Ryzen 3? Is it a Ryzen 3 or Ryzen 5? We're hiring software engineer who know programming language Rust. Yeah. Count me in. Trump conspiracies have mega world talking Georgia boycott? Oh, come on. Oh. Two GOP candidates, Kelly Loeffler, David Perdue, are not only insufficiently pro-Trump, maybe complicit? Oh, come on, guys. The runoff is gonna be the real battle because it will basically set the tone for the next 2 years. If the Democrats have the Senate, then they will have an easy path forward. But if they don't have the Senate, then well, they have to. Think Republicans have the Senate, 50 in the Senate, yeah. So Democrats have to get both two. I mean, other parties have 2 seats, but do they vote Republican? No. What? What's this? Senate. Lawsuit. I don't think this will go anywhere. Yeah. Watch other parties that have. Who cares? But this is Ryzen 5. Huh? What? Ryzen 5000 AP laptop. This laptop backs AMD Ryzen 5000 desktop processor. AMD Ryzen 7 5800U leak suggests superb laptop chip that could blow away into. Origin has removed the Ryzen 5000 processor option from their website. It's currently only available on Ryzen 3000. Okay. Is it the Origin again? No, Acer. 5700U could be based on. Okay. A new and unannounced. Okay. Means a rumor. So Zen 3 5400U. What? Okay. So the even number here, the second number, if it's even, this is on. Oh, this is Ryzen 3. Yeah. Yeah, that makes sense. That makes sense. Although doesn't show how many GPU are. Okay. I should just await my own Gen 2. Okay. Let's continue. F expression. An F expression allows you to branch code. So F, no parentheses. Branches, okay, no parentheses. Less than, sure. Followed by condition, in this case condition, whether variable number. The code block is associated with expression. Okay. Comparing the guess to secret number, yeah, sure. Optionally, else expression, what you do have here, okay. Yeah, optionally, we can also include an, okay. If you don't provide an else expression and the condition is false, the program will skip the if block and move to the next bit of code. Okay. Condition in this code must be a boolean. If condition isn't boolean, we'll get an error. That's good. No guessing with what values are false, what values are okay. Unlike language Ruby, JavaScript, Rust will not automatically try to convert non-boolean types as a boolean. You must be explicit and always provide f with a boolean condition. That's good. If you want, okay. Handling multiple conditions with else if. Sure, else if. Okay. For possible paths. When the program executes, check it. Okay. Using too many else if expressions can clutter your code. Match, yeah. Using if in a lit statement. Then you have to provide both else, yeah. And semicolon, of course. Yeah. Number value won't be bound to value. Okay, of expression card will run. Okay, remember that blocks of code evaluate the last expression in them, and numbers by themselves are expression. In this case, all if. Okay. This is all easy. This will be a problem because the type is different. Evaluate integer and blocks the value as one because variable must have single type. Yeah. Must not be able to do that. Okay, was only to the compiler would have repetition with loops. Useful to explain, execute a block. Oh, it's stop update. Okay. Yeah. Loop, while, and for. Loop again over and over until you explicitly tell it to stop. Control C. Yeah. Fortunately, Rust provides another more reliable way to break out, which is break. I think after correct this, yeah, turning values from loops. One of the uses of a loop is to retry an operator. Oh, so you can provide a you might need to pass the result, yeah, to the result. Yeah, to do this you can add, okay, with the break expression. Nice, that's a good one. For the loop declared, counter initialized to 0. Result. Let the result be a loop, and when it breaks, it's counter times 2. That's nice. While it's open. Okay. This term, yeah, if else break. Looping through collection with for. Let A be a, yeah, an array. Let mutable index be 0, while index less than 5, print, yeah, and have to increment the index. Yeah, that sucks. Here, counts up the elements. Yeah, sure, one of the true. All 5 arrays appear to be terminal, sure. But this approach is error prone. We could cause the program to panic if the indexes, yeah. It's also slow because the compiler adds runtime code to perform conditional check on every element on every iteration through the loop. A more precise, concise alternative you can use for loop and execute, yeah, an iterator for n iterator, yeah. When we run this code, we'll see the same output. More importantly, we've now increased the safety of the code and eliminated the chance of bugs that might result. Okay. The safety and conciseness of for loops make them most commonly used loop constructs in Rust, even in situations when you want to run some code a certain number of times, as in countdown example in while. For loop, the way that should be user in range, okay, which is type of unassigned library. It generates all number sequence, okay, and ending before another number. Here's that countdown for number in 1 to 4 dot reverse, yeah, 4 3 2 and lift off. This will not yeah, this will be 1 to 3 1 2 3 reverse 3 2 1, right? I believe it's gonna be 3 2 1 off. Yeah. Summary, you made it. Sizable chapter, you learn variable scale component if expressions. If you want to practice with concepts and discussing it, you try building programs to do the following: convert temperature between Fahrenheit and Celsius, generate the nth Fibonacci number, print the lyrics to the Christmas Carol, the 12 Days of Christmas, taking advantage of the repetition in the song. Let's do the When you're ready to move on, we'll talk about a concept in Rust that doesn't commonly exist in other programming languages: ownership. On the first day of Christmas, my true love sent to me. On the second day of Christmas, on the third day of Christmas, 3 French hens, 2 turtle doves, and a partridge in a pear tree. That's enough. I'm not gonna. Okay. For day and present in order, print ln on the day of Christmas, my true love sent to me. Um, okay. This should be okay. For day present in order. I'm not sure if this will work. I'm not sure if the string comparison will work or not. Cargo run. Yeah. Let order be oh. Okay. Borrow the array with and or call dot iter. Oh, dot iter. Okay. Thank you, Rust compiler. Will the yeah. partial equal. We could do length of present greater than 0. For now, before. Yeah. On the first day of Christmas, my true love sent to me partridge in a pear tree. On the second day of Christmas, my true love sent to me two turtle doves and a partridge in a pear tree. Yes. These spaces are not correct. Okay. So one down in Fibonacci number. Does this work? Can we do it in a tuple kind of way? these should be flipped. So I will be priv1 plus priv2. Priv1 will be priv2. Priv2 will be I. Does this provide us with fib num so return I. I'll remove these parentheses. Sure. What is it that they have problem with? Colon equals symbol with a colon while parsing this struct. All of them are I32, aren't they? If I do this, does this work? Cannot assign to this expression. Deconstructing arguments are unstable. Okay. Okay, so first, let's do this. Is there not tuple assignment? Yeah, it's possible. What is going on? Only in initialization? Okay, let's do this. I let temp equals I yeah, prev1. Oh, I equals prev2 plus prev1. Ah, come on. Prev2 equals to temp. Prev1. Oh, prev1 equals to temp. Prev2 equals to I. Ah, prev1. Jesus Christ. Prev2 is equal to prev1. Yeah. Is this okay now? It doesn't take an iterator. Okay. Temp is equal to I. Oh, no, 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 no. Should be something like this. Previous equals 0. Let mutable I equals 1. Okay. Actually, it should be yeah, it should be 1. Actually, it mutable. Next equals 1. Next and I. Next and I equals next plus I, comma, next. This should be it. Again, for some reason they don't like. Do I have to say let? Can I assign? Let temp equals next. Next equals I plus I. Next I equals temp. And return I. Yeah. Fifth Fibonacci should be 3. 0, 1, 0, 1, 1, 2, 3, 5. 1, 2, 3, 4, 5. Yeah. Index 15. 377. Yeah. I wonder if I can do it in fn fib 2 n I32 I32. Let's see. So we need and this is zipped together with dot take fold oh no, it's not gonna be like this. It's gonna be let's think about it, how to do it in a functional style. Could be a zeros. So I don't want to. So I could do fold left, fold. I'm not sure if I think it's 1.n but fold. I'm not sure. So what I have, I would have to have, this is the initial position, and it would be comma and I coming from this here. I would completely discard the I, but I would do this like this would expect so this is the sum and this is I. I would do, oh, so it's more like it's like I comma next. Okay. And I would do this. This would be next. And this would be I. Next. And this would be next plus I. And completely discarding the second. Let's see. Rust. Fold. Is there a fold operation? Fold. Yeah. Fold first. Fold. An iterator method that applies function producing a single final value. Fold takes two arguments, an initial value and a closure with two arguments, a cumulator and an element. The closure, oh, so this is the closure syntax. Okay. So it would be something like this. Nope. Like this. Oh, come on. Yeah, I don't care what it gives me, but what I return is this. Yeah. And the initial value would be 0, 0, 0. And actually would return the first item. Let's see. Expected curly brace. No, it's correct. Ah, there's no. 600. Yeah, okay. 610. 1, 2, and fold. Let's give should be from 2. Always 1. Oh, 0. Yeah, first argument is always 0. Let's do 15 again. It's gonna be 337. 377. Yep, correct. This is the second one. Okay, fold first. Fold first, the same as fold, but uses first element in the iterator as the initial value. Okay, sure, yeah. Folding every subsequent element into itself. The iterator is empty. That's nice. Cool. Cool. Convert temperature, that's easy at this point. Sure, let's do it. It's easy. It's divided by, yeah, no. Okay, ownership. Ownership is Rust's most unique feature, and it enables us to make memory safety guarantees without needing garbage collector. Therefore, it's important to understand how ownership works in Rust. In this chapter, we'll talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. Okay. Don't need these. Any news? Yeah, okay. Iterator. How many traits are there in the Rust standard library? How many traits are there? Modules. Macros, keywords. Keywords. Is mod a keyword? Yeah. Oh, module. Huh. Rest modulus. Is it a modulus, not a remainder function? As far as I can, there's no module. This also happens as 3. Walk around. Okay. A modulus B plus add a whole B modulus B. Remainder, yeah. So this takes care of the. But this is only if B is positive. If B is negative. Oh no, it works. Yeah. Rust traits. Steady traits. Common Rust traits. Okay, we got that. Okay, let's go back. Understanding ownership. Important to understand how ownership works. In this chapter, we'll talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. What is ownership? That's a lengthy chapter. Okay. Rust's central feature is ownership. Although the feature is straightforward to explain, it has deep implications for the rest of the language. All programs have to manage the way they use a computer's memory while running. Some languages have garbage collection that constantly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks at compile time. None of the ownership features slow down your program while it's running. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that the more experienced you become with Rust and the rules of the ownership system, the more you'll be able to naturally develop code that is safe and efficient. Keep at it. When you understand ownership, you have a solid foundation for understanding features that make Rust unique. In this chapter, you will learn ownership by working through some examples that focus on very common data structures, strings, the stack, and the heap. In many programming languages, you don't have to think about the stack and the heap very often. But in a systems programming language like Rust, whether a value is on the stack or the heap has more of an effect on how the language behaves and why you have to make certain decisions. Part of ownership will be described in relations to the stack and the heap later in this chapter. So is a brief explanation in preparation. Here is a brief explanation. Okay. Both the stack and the heap are parts of memory that are available to your code to use at runtime, but they are structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order, first in, last in, first out. Think of stack plates, add more plates, you put them on top of the pile. When you need a plate, you take one off the top. Adding or removing plates from the middle or bottom wouldn't work well. Adding data calling is called pushing onto the stack, removing called popping off the stack. All data on the stack must have a known fixed size. Data with an unknown size at compile time or size that might change must be stored on the heap instead. The heap is less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough, marks it as being in use, and returns a pointer, which is the address of the allocation. This process is called allocating on the heap, and is sometimes abbreviated just allocating. Pushing values onto the stack is not considered allocating because the pointer is known, fixed size. You can store a pointer on the stack, but when you want the actual data, you must follow the pointer. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the staff finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you have been seated to find you. Pushing to the stack is faster than allocating on the heap because the allocator never has to search for a place to store the new data. The location is always at the top of the stack. Comparatively, allocating space on the heap requires more work because the allocator must find a big enough space to hold the data and then perform bookkeeping to prepare for the next allocation. Accessing the data in the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are fast if they jump around list in memory. Continuing the analogy, consider a server at a restaurant taking order from many tables. It's most efficient to get all the orders at one table before moving on to the next table. Taking an order from table A, then an order from table B, then one from A again, and then one from B again would be a much slower process. By the same token, a processor can do its job better if it works on the data that is close to the other data, as it is on the stack, rather than further away, as it can be on the heap. Allocating a large amount of space on the heap can take time. When your code calls a function, the values passed into the function, including potentially pointers to the data on the heap, and the function's local variables get pushed onto the stack. When the function is over, those values get popped off the stack. Keeping track of what parts of code using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space. All problems ownership addresses. Once you understand ownership, you won't need to think about stack and the heap very often, but knowing that managing heap data is why ownership exists can help explain why it works the way it does. Ownership rules. First, take a look at the ownership rules. Keep these rules in mind as we work through the examples that illustrate them. Each value in Rust has a variable that is called its owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Variable scope. We've talked about an example Rust program already in chapter 2. Now we're past basic syntax. Won't include all the if and main code in following along. As a result, our example will be a bit more concise, focus on the detail. First, ownership, scope of variable. Scope is the range within the program which an item is valid. Let's say that you have a variable. Okay, let s equals 0. Variable s refers to a string literal, where the value of the string is hard-coded into the next text of our program. The variable is valid from the point at which it is declared until the end of the current scope. Okay, do stuff with this. Stuff is not valid here. It's not yet declared. S is valid from this point forward. Do stuff with S. This scope is now over and S is no longer valid. In other words, there are two important points here. When S comes into scope, it is valid. It remains valid until it goes out of scope. At this point, the relationship between scopes and when the variable is valid is similar to that in other programming languages. Now we'll build on top this understanding, introducing the string type. To illustrate the rules of ownership, we need data that is more complex than ones covered in data types section. The types covered previously are all stored on the stack, popped off the stack when the scope is over, but we want to look at data that is stored on the heap and explore how Rust knows when to clean up that data. We'll use string as an example and concentrate on parts of the string that relate to ownership. These aspects also apply to other complex data types, whether they are provided by a standard library that or created by. We'll discuss string in more depth in chapter 8. Okay, so this version. We've already seen string letters where let's check. Don't have any. We've already seen string literals where string values hard-coding output. String literals are convenient because they aren't suitable, but they aren't suitable for every situation in which we may want to use text. One reason is they are immutable. Another is that not every string value can be known when we write our code. For example, what if you want a user input and store it? For this situation, Rust has a second type string. This type is allocated on the heap and as such is able to store an amount of the text that is unknown to us at compile time. You can create a string from a string literal using the from function, like so. String from hello string literals. String from hello. The double colon is an operator that allows us to namespace this particular from function under the string type rather than using some sort of like string from. We'll discuss this more in method syntax, section chapter 5. Talk about namespacing with modules in chapter 7. Let mutable s equals string from hello. Okay. S dot push string appends a literal to a string. This will print hello world. What's the difference here? Why can string be mutated but literals cannot? The difference is how these two types deal with memory. S the poster. Okay. Memory allocation. In the case of a string literal, we know the contents at compile time, so the text is hard-coded directly into the final executable. This is why string literals are fast and efficient, but these properties only come from string literals' immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time, and whose size might change while running the program. With the string type, in order to support mutable, growable piece of text, we need to allocate an amount of memory on the heap unknown at compile time to hold the contents. This means the memory must be requested from the memory allocated at runtime. We need a way of returning this memory to the allocator when we're done with our string. The first part is done by us. When we call string from, its implementation requests memory it needs. This is pretty much universal in programming languages. However, the second part is different. In languages with a garbage collector, the GC keeps track and cleans up memory that isn't being used anymore. And we don't need to think about it. Without a GC, it's our responsibility to identify when memory is no longer being used and call code to explicitly return it, just as we did request it. Doing this correctly has historically been difficult. A difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, it's a bug. We need to pair exactly one allocated with exactly one free. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our example listing for one string instead of string literal. String is valid to do stuff, no longer valid. This is a natural point at which we can return memory. Our string needs the allocator when s goes out of scope. When a variable goes out of scope, Rust calls a special function for us, a function called drop, and it's where the authors of string put the code to return the memory. Rust calls drop automatically at closing curly braces. Known in C++, this pattern of deallocating at the end of an item's lifetime is sometimes called resource acquisition is initialization. Pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition is initialization. The drop function in Rust will be familiar to you if you use the right pattern. Resource acquisition is initialization. Idiom used to verify. Class invariant is used to object lifetime. I don't understand. Anyhow, this pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of the code can be unexpected in more complicated situations when we want to have multiple variables use the data we've allocated on the heap. Let's explore some of these situations now. Ways variable and data interact. Move. Multiple variables can interact with the same data in different ways. Let's look at an example. Let x equals 5, let y equals x. We can probably guess that this is going to be bind value 5 to x, then make a copy of the value in x and bind it to y. We now have two variables, x and y, both equal 5. This is indeed what is happening because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. Now let's look at the string version. Let s1 string hello, let s2 equals s1. This looks very similar to the previous code, so we might assume that the way it works would be the same. Second line would make a copy of the value in s1 and bind it to s2, but this isn't what happens. Take a look at figure 4.1 to see what's happening in string under the cover. A string is made up of 3 parts, shown on the left. A pointer to the memory that holds the contents of a string, length, and a capacitor. This group of data is stored on the stack. On the right is the memory on the heap that holds the content. The length is how much memory in bytes in the contents of the string is currently using. Capacity is total amount of memory in bytes. String, okay. The difference between length and capacity matters, but not in this context. For now, it's fine to ignore capacity. When we assign S1 to S2, the data is copied, meaning we copy the pointer to the length and the capacity to the pointer, the length and the capacity on the stack. But we do not copy the data on the heap that the pointer refers to. In other words, the data representation in memory looks like this. The representation does not look like figure 4.3, which is, yeah. If Rust did this, the operation S2 equals S1 would be very expensive in terms of runtime performance if data is on the heap very large. Okay. Earlier we said that when a variable goes out of scope, Rust automatically calls drop function and cleans up the heap memory for that value. But figure 4.2 shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they both will try to free the same memory. This is known as double free error and is one of the memory safety bugs we mentioned previously. Failing freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerability. To ensure memory safety, there is one more detail to what happens in this situation in Rust. Instead of trying to copy the allocated memory, Rust considers S1 to be copy the allocated memory. Rust considers S1 to no longer be valid, and therefore Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when we try to use S1 after S2 is created. It won't work. Let S1 equals string from hello. Let S2 equals S1. Okay, so this will not work. You'll get an error because Rust prevents you from using invalidated references. Value borrowed here after move. If you've heard the term shallow copy and deep copy while working with other languages, the concept of copying the pointer length capacity without copying the data probably sounds like making a shallow copy, but because Rust also validates the first variable instead of being called a shallow copy, it's known as a move. This example, we would say that S1 has moved into S2. So what actually happens is shown in figure 4.4. That solves our problem with S2 with only S2 valid. When it goes out of scope, it alone will free the memory and we're done. In addition, there is a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Okay. Ways variables and data interact. Clone. If we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone. We'll discuss the method syntax in chapter 5, because methods are a common feature in many programming languages. You've probably seen them before. S1.clone. Now this works fine and explicitly produces the behavior shown in figure 4.3, where the heap data does get copied. Okay. When you see call to clone, you know that some arbitrary code is being executed, and that code may be expensive. It's a visual indicator that something different is going on. Stack only data copy. There's another wrinkle we haven't talked about yet. The code using integers, part of which was shown in listing 4.2, works and is valid. X equals 5, Y equals X, print X and Y. But this code seems to contradict what we just learned. We don't have to call to clone, but X is still valid and wasn't moved to Y. The reason is that types such as integer have a known size at compile time and are stored entirely on the stack, so copies of the actual values are quick to make. That means there is no reason we would want to prevent X from being valid after we create a variable Y. In other words, no difference between deep and shallow copying here. So calling clone wouldn't do anything different from the usual shallow copying, and we can leave it out. Rust has a special annotation called the copy trait that we can place on types like integers that are stored on the stack. We'll talk more about traits in chapter 10. If a type has copy trait, an older variable is still usable after the assignment. Rust won't let us annotate a type with copy trait if the type or any of its parts has implemented the drop trait. If the type needs something special to happen when the value goes out of scope, we add copy annotation to that type. If the type needs something special to happen when value goes out of scope, we add the copy annotation to that type. We'll get compile time. What? If the type needs something special to happen when the value goes out of scope and we add the copy annotation to that type, we'll get a compile time error. To learn about how to add the copy annotation, see derivable traits in Appendix C. So what types are copy? You can check the documentation and give type for the given type to be sure, but as a general rule, any group of simple scalar values can be copy, and nothing that requires allocation or is some form of a resource is copy. Here are some of the types that are copy. All integer types, Boolean, floating points, character, so all the scalar. Tuples if only contains types that are also copy. Okay. Ownership and functions. The semantics for passing a value to a function are similar to those assigning value to a variable. Passing a variable to a function will move or copy, just as the assignment does. Listing 4.3 has an example with some annotation showing where variable goes into and out of scope. Okay, takes ownership. This takes ownership. Let x equals 5, makes copy 5. S comes into scope. S's value moves into the function and so is no longer valid here. X comes into scope. X would move into the function, but I is a copy, so it will still be okay afterwards. X goes out of scope, then because S's value was moved, nothing special happens here. Some string comes into scope, goes out of scope, memory is freed. Yeah. If we try to use S after the takes ownership, Rust would throw a compile time error. These static checks protect us from mistakes. Try adding code to the main, use S and X, see where you can use them and where the ownership rules prevent you from doing so. Okay, return values and scope. Returning values can also transfer ownership. Listing 4.4 is an example with similar annotations. Okay. Gives ownership. Yeah, makes a string here, some string, gives ownership. S2 takes and gives back a string, takes and gives back. Yeah. The ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes the data on the heap goes out of scope, the value will be cleaned up by a drop unless the data has been moved to be owned by another variable. Taking ownership and then returning ownership with every function is a bit tedious. What if you want to let a function use a value but not take ownership? It's it's quite annoying that anything we pass in also needs to be passed back. If we want to use it again, in addition to any data resulting from the body of the function that we might want to return as well, it is possible to return multiple values using a tuple as shown. Okay. Calculate length and return the string and the length again. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for this concept called references. Okay. Just a little break. Nothing in the chat. Okay, let's continue. References and borrowing. The issue with the tuple code listing 4.5 is that we have to return string to the calling function so that we can still use a string after the call to the calculate length, because string was moved into calculate length. Here is how you would define a calculate length function that has a reference to an object as a parameter instead of taking ownership to the value. Ampersand string, and you pass ampersand s1. First, notice that the tuple code in the variable declaration and the function return is gone. Second, note that we pass and s into calculate, and its definition we take and string rather than string. The ampersands are references, and they allow you to refer to some value without taking ownership of it. So s would be a pointer to s1. Note the opposite of referencing by and is dereferencing, which is accomplished with the dereference operator with star. We'll see some use of the dereference operator in chapter 8. discuss details of differences in chapter 15. What is 8? 8 is common collections. 15 is smart pointers. Okay. Let's take a closer look at the function called here. Let S1 be a string. Let len be calculate length and S1. The and S1 syntax lets us create a reference that refers to the value S1 but doesn't own it. Because it doesn't own it, the value it points to will not be dropped when the reference goes out of scope. Likewise, the signature of the function uses AND to indicate that the type of a parameter S is a reference. Let's add explanatory annotation. The scope in which the variable S is valid is the same as any function parameter scope, but we don't drop the reference points to it when it goes out of scope because we don't have ownership. Well, when functions have references as parameters instead of the actual values, we won't need to return the values in order to give back ownership because we never had ownership. We call having references as function parameters borrowing. As in real life, if a person owns something, you can borrow it from them. When you're done, you have to give it back. So what happens if we modify something we're borrowing? Try the code. Okay, change S, push string world. It will be an error. Yeah, refers to cannot be borrowed as mutable. Just as variables are immutable by default, so are references. We're not allowed to modify something we have a reference to. Mutable references. We can fix the error in the code from 4.6 with a small tweak. And mutable. First, we had to change S to be mutable, then we had to create a mutable reference with and mutable and accept a mutable reference with some sort. But mutable references have one big restriction. You can only have only one mutable reference to a particular piece of data in a particular scope. This will fail. Let S be a string, mutable S. R1, the mutable reference to S. R2, mutable reference to S. Borrow later used here. This restriction allows for mutation, but in very controlled fashion. It's something that new rustaceans struggle with because most languages let you mutate whenever you want. You'd like. The benefit is having restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is being used to write to the data. There is no mechanism being used to synchronize access to the data. Data races can cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Rust prevents this problem from happening because it won't even compile code with data races. As always, we can use curly brackets to create new scope, allowing for multiple mutable references, just not simultaneous ones. Yeah. R1 goes out of scope, we can make a new reference with no problem. A similar rule exists for combining mutable and immutable references. This code results in an error, and no problem, but an mutable big problem. We also cannot have a mutable reference while having an immutable one. Users of an immutable reference don't expect values to suddenly change from under them. However, multiple immutable references are okay because no one who is just reading the data has the ability to affect anyone else's reading of the data. Note that a reference scope starts where it is introduced, but here's the problem. This is also mutable, right? So if let's say I have a thread here, and I have a thread here, would that be allowed? It's mutable here, like spawn a thread here, and anyhow, it's too early for threading now. Note that reference scope starts where it is introduced and continues through the last time that reference is used. Reference scope starts from where it is introduced and continues through the last time that reference is used. For instance, this code will compile because the last usage of the immutable reference occurs before the mutable reference is introduced. Are no longer used at this point. Yeah. The scopes of immutable references are when after println where they last used, which is before mutable reference the R3 create. The scopes don't overlap, so the code is allowed. Even though borrowing errors may be frustrating at times, remember that it's Rust compiler pointing out potential bug early at compile time rather than at runtime, and showing you exactly what the problem is. Then you don't have to track down why your data isn't what you thought it was. Dangling references. In languages with pointers, it is easy to erroneously create a dangling pointer that references a location memory that may have been given to someone else by freeing some memory while preserving a pointer to their memory. In Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. Reference nothing, dangle. Let s, okay, string, and return a reference. It will say, consider giving it static lifetime and static. Okay. The error message refers to a feature we haven't covered yet, lifetimes. We'll discuss lifetimes in detail in chapter 10, but if you disregard the part about lifetime, the message contains key why the code is problematic. The function return contains borrowed value, but there is no value for it to be borrowed from. Let's take a closer look what's happening. Yeah. Dangle returns a reference to a string. S is a new string, we use a reference here. Here S goes out of scope and its dropped memory goes away. Danger. Because S is created inside dangle, when code of dangle is finished, S will be deallocated. But we try to return a reference to it. This means the reference would be pointing to an invalid string. That's no good. Rust won't let us do that. Solution is to return the string directly. This works without any problems. Ownership is ruled out and nothing is deallocated. Rules of references. Let's recap. At any given time, you can have either one mutable reference or any number of immutable references. References must always be valid. Different kind of reference slices. Just a small break. Need to check something.